So let's go ahead. Let's write the test. My governor test.t.sol. And the other reason that I'm going a little bit quicker here is because at this point, you understand a lot of this, right? And you know and should know how to go back and flesh this repo out, right? With scripts, with tests, unit tests, fuzz tests, etc. And you know how to make this project badass. And I just want to give you the new stuff, right? Teach you the new stuff for here. Teach you about the DAO stuff. So let's write some tests just so that we can really see this process work end to end. And we're just going to have one giant test just to show the whole process. So you know the drill. Pragma Solidity here. Contract my governor test is test. You already know we're going to import test from forge std / test.sol. And we're going to need a function set up. It's going to be public, of course. And we're going to need a whole bunch of stuff in here. Function setup. Oops. What are we going to need? Well, we're probably going to need at least these 4 contracts. So let's go ahead and import them. Import my governor from / src / my governor.sol. Import box from / src / box.sol. Import time lock from here. GitHub Copilot taking over a little bit. Import gov token. Okay, it failed. It almost took over here from / src / gov token.sol. Oh, is that not what it's called? Sorry. Let's change this into gov token. Like this. That's good. Okay. So now let's actually deploy some of these. So our gov token, we'll say, actually, let's create each one of these. My governor, box, time lock, gov token. Cool. First thing that we're going to need is our gov token equals new gov token. And I know this doesn't take any input parameters, but we should give our gov token, we should actually mint some of these. This gov token doesn't have a mint function. So I'm just going to create a mint function, but in your system, maybe you just have the constructor mint to the message.sender. I'm just going to go ahead and add this function mint address to UN256 amount. We'll make this public. This probably isn't what you want your token to have. You probably don't want anyone to be able to mint any tokens, but this is what I'm going to do. Mint to amount. That's it. There's an internal function called mint that we're going to call. So I'm just going to say, I'm going to mint it to some user. I'm going to say address public user equals make address. This is going to be our user here. Do this capitals user like this. We're going to say gov token.mint user, and we'll do UN256 public constant. Initial supply equals 100 ether. So we're going to mint ourselves 100 ether. Boom. All right, cool. Now, something that you'll often forget is that just because you minted tokens doesn't mean you have any voting power. So we want to run gov token.delegate, that delegate function, and we're just going to delegate to ourselves. So we're saying, hey, we now have 100 tokens. We're going to delegate those 100 tokens voting power to ourselves. You could delegate it to somebody else if you wanted to, but for our test, we're going to do it for us. And we need to actually do vm.start prank user, because only the user can delegate tokens to themselves. And we might as well stay as the user for these next ones, just that we can start off as owners of the contracts we're about to do. So now that we have our governance token, next what we want to deploy is our time lock. Because in order to deploy our governor, we're going to need both the gov token and the time lock. So we have the gov token. Let's actually create the time lock now. So we're going to say time lock equals new time lock. And what does this take? Min delay, proposers, executors. So let's create those. I'm going to scroll up. We're going to make UN256 public constant min delay equals 3600, which is going to be 1 hour. This is the delay after a vote passes, right? So this is the time lock's min delay. Nobody can actually execute a past proposal until an hour goes by. Boom, we'll do min delay. What else do we need? We need the proposers for stuff. And we'll just make this at the top, address array proposers, address array executors. And we'll just leave it blank because we don't care. Proposers, executors. And this is actually how, with the time lock controller, you say anyone can propose and anybody can execute. You just leave these arrays blank. Cool, looks good. Okay. Now that we have that, we finally can deploy our governor contract because we have these two. So we'll say what do we call it? Do we just call it governor? Yep. Governor equals new my governor gov token time lock like that. Now we have to grant some roles. So the time lock actually starts with some default roles, and we need to grant the governor a whole bunch of roles, and then we need to remove ourselves as the admin of the time lock, right? We don't want a single centralized entity to have power over it. So first we got to get some of the roles. So we're gonna say bytes32 proposer role. And the way that the time lock has roles is that it hashes the names of stuff. So we'll say proposer role equals time lock proposer role. So there's this function on the time lock called proposer role. And we're gonna allow this proposer role to be just the governor. So only the governor can propose stuff to the time lock. We're gonna say bytes32 executor role is gonna be time lock.executor role. We're gonna give this to anybody by setting it to the 0 address, and then bytes32 admin role. Right now that's us. Time lock nope, it's gonna be time lock admin role. And so, like I said, these are just kind of the these are hashes in the time lock, and we just need to update these. So we're gonna say time lock dot. It has a grant role function. We're gonna grant this proposer role to the governor, so only the governor can actually propose stuff to the time lock. Or say time lock dot grant role executor role to address 0, which means anybody can execute a past proposal. And then time lock dot revoke role, revoke the admin role from user. So the user will no longer be the admin. And then we'll say vm.stop prank this. And then we just need a new box. Box equals new box. And now we're going to transfer ownership of the box to the time lock. And the time lock is owned by the DAO. So we're going to say box.transfer ownership to address time lock. So transfer ownership. A common misconception here is, oh, shouldn't we transfer to the DAO? No, we should transfer to the time lock. So the time lock owns the DAO. So the time lock owns the DAO and the DAO owns the time lock. It's kind of this weird two-way relationship, but it's the time lock that gets the ultimate say on where stuff goes. So we transfer it to the DAO. And so we can even do a quick test. Function test can't update box without governance. Public. We'll say vm.expect revert box.store 1 like this. Since our box has a store function that's only owner, the owner is now the time lock / the DAO. Oops. If I try to run this test, right, forge test-m, paste this in, this should pass because you can't update the box unless it's through governance. And this will also be our sanity check to make sure all of our code is compiling, which it is. Okay, great. Let's keep going. So now let's make a giant function test governance updates box public. And this will show you the exact process from a code standpoint of how one of these DAOs actually work. So first, let's get started. Uint 256 value to store is going to be 888. Boom. So we're going to update our box, right? This box here, we're going to update this new number to 888. Okay. Let's come up with a proposal, right? Remember, if we show up my governor, we click into governor, and we click into governor function propose. right here. First thing we need to do to kick off anything is propose something. Hey, we are going to propose that box updates the stored value to 888. So we're going to need to have all this stuff in here. Targets, values, call datas, descriptions. So let's start with description because that's simplest, right? String, memory, description equals store one in box. That's it. That's our description. Pretty easy, right? What else do we need? Okay, we're going to need some call datas. Oh, well, we know what call datas are. That's that function selector and all that other stuff that we learned in that NFT one, right? So we can say bytes memory. So if you go back to the Foundry NFT F23, we go to SRC, sublesson, we can remember, oh, wait, we can call anything that we want, right? And all we got to do is encode stuff, right? Like abi.encode with signature or encode with selector or whatever we want to do here. So we can actually say, oh, okay, so this allows us to make any function call that we want. So we'll encode it by saying encoded function call equals, what do we want to call? Well, we want to call this store function. So we know the function signature of store is going to be store uint256. So we can say abi.encode with signature. We're going to call the store function like this. And then what else do we need? Well, we need the value like this, and that's it. Cool. Let me toggle the word wrap here. Cool. So we have the encoded function call. So we have the call datas that we need to call it. Okay, great. What do we need next? And we're going kind of in this reverse order. Values. Well, we don't really care to send any value, right? So let's even just go to the top here. We'll make a uint256 array values. It'll start off as blank. We'll just say values.push 0. Cool. We'll just have it be empty. We're not going to send any ETH. And then the final thing we need is targets. So we want to call this on the box contract, right? Oh, and actually, call datas is also an array. So we're going to do a couple things. We're going to do values, call datas, and targets. Targets, right? So the call datas is a uint256. No, call datas is a bytes array. And targets is an address array. So we're going to say values.push 0, call datas.push that encoded function call that we just made, and then targets.push the address of the box, right? So now we have all that. Now we can finally call our propose function. And what does this propose function return? It returns this uint256 proposal ID, and we need that to keep going. So first thing we're going to do is propose to the DAO. Propose to the DAO. So say uint256 proposal ID equals governor.propose the targets, values, call datas, and description. Boom. And we get our proposal ID just like that. Now we can even view the state of this proposal now, right? Because we can call that state function. So we can do even like a little console.log proposal state. We can call a state function like this. Actually, GitHub Copilot has this right, except for we want to turn this into the uint256 version. So we'll say uint256 governor.state proposal ID like this. And if we look up function state, we'll find this. There's like a million of these. In our governor.sol, it returns this proposal state, which if we control or command click on that, we can see all the different states it can have. Pending, active, canceled, defeated, succeeded, queued, expired, executed. So pending obviously is going to be 0. Active is obviously going to be 1. Canceled is going to be 2, etc. Right? And of course, we're going to need to import console from test. Okay, cool. So this should return what? Should return pending. It should return a 0. And it hasn't started yet. It's not active because there's a delay, right? So we want to actually update our fake blockchain to move past that. So we'll just do vm.warp. We'll use these cheat codes, remember? Block.timestamp plus, and then we'll just do voting delay, uint6 public constant voting delay equals 1. This is how many blocks till a vote is active, right? And from our wizard, we just left this as 1. Oh, well, if we go back to governor, we just left our voting delay as 1. So this voting delay is 1. So plus voting delay. And then actually we'll do voting delay plus 1. And then we'll also do roll to increase the time as well. vm.warp, or excuse me, to increase the number, block.number plus voting delay plus 1. Now, if you view the state, it should be active. So now it'll be active. Cool. 2, after a proposal starts, because we've proposed, enough time has passed, we now can actually start voting on something. So I'm going to do this cast vote function, but I'm going to do cast vote with reason because I like cast voting with a reason. So we're going to do string memory reason equals, because blue frog is cool. That's going to be my reason. That's why I'm going to vote for something, because blue frog is cool. In order to vote, we're going to need to call this cast vote function. And if we go to governor, we'll look for the function vote, or excuse me, cast. If we go in our search bar, we can look for function cast vote. There's a whole bunch of cast votes. We can see in here, we need to pass a proposal ID and support. How do we know support works? Well, let's look at this cast vote internal function. This cast vote internal function down here, support count vote. We got to look at this count vote function. So let's look for function count vote. Okay, this is the abstract implementation. We don't want governor compatibility Bravo. We want governor counting simple because that's what we're using. Okay, support, how does support work? Aha, okay. So there's this vote type struct that it's checking for. Let's go to the vote type. Okay, against, for, abstain. So against is going to be 0. For is going to be 1. And abstain is going to be 2. So what do I want to do? I want to write vote for. So we're going to do 1. So we're going to say we have our reason. Uint 8 vote way equals 1, which means I'm voting for, voting yes, if you will. And now let's do our vm.prank, our user or our voter, and we'll do governor.cast vote with reason, proposal, ID, vote way, and reason. Reason. All right, cool. Now that we've voted, let's speed up this voting period because everyone voted because we're the only voter. Let's speed up this voting period. And we set the voting period automatically. If we go back to our my governor, right? Voting period was set to 1 week. In here, this number represents 1 week. So we're going to speed up this voting period. I'm going to copy this number, scroll up to the top. We'll do uint 256 public constant, voting period equals this. Oh, and this should have a semicolon. Voting period. We're going to speed through the voting period. I'm going to just copy these, change this to voting period. Voting period. Now that we've voted and the voting period is done, what do? Well, we actually need to queue the TX before we can actually execute. So we have to queue it first. So there's a queuing process. So on our my governor, there's a function queue, and a whole bunch of them have this. Let me open this up. Function queue. On this governor time lock controller, there's this queuing bit because a queue means it's passed, but we have to wait to queue it up. We just pass the same bits that we originally did for propose. So we're going to go back here. We'll say the only difference is we need to hash the description first. So we'll say bytes 32, description hash equals get check 256 abi.encode packed description. Now we can call governor.queue proposal ID. This is not right. Governor.queue targets. We're going to pass the same values that we proposed with so that we guarantee it's the same proposal. So targets, values, function, call datas and description hash. Oh, we don't need that 0. We're going to queue it. And then we're going to finally wait this min delay, which we said, hey, after a vote passes, we need to wait this min delay before we can execute. So I'm going to copy this again, paste it here. Instead of voting period, this is going to be min delay. And then finally, we can execute. So we'll do governor.execute. It's going to be the same as what we did to queue it up. I even just copy this whole thing, paste it here. Targets, values, call data is description hash. Let me spell this right. And now finally, we can do assert box dot get number equals the value that we stored. Boom. We can even do like a console.log, box value, box.get number. Okay. Copy this, open our terminal, clear, forge, test, -m, paste, -vv, so we can see the console.logs. Pull it up. Is this what we've been waiting for? No, we ran into an issue. We see these 2 logs, proposal state is 0. We're getting vote currently not active. So let's add a couple more V's so we can see where it failed. It looks like it got to the cast vote with reason and it failed. So let's go to our test. So it looks like it proposed okay. It looks like this failed. So it says it's currently not active. So did we mess up our voting delay? It's because I did warp for both. This should be vm.roll. And let's see, oh, we messed that up for all of them. Let's fix this. Roll. Okay, cool. That's clear. Let's run it again. Pull this up. Oh my goodness, it passed. And we can see in the logs, proposal state was 0. We waited and then it became inactive. And then finally, after we got through all the different states, we finally were able to update the box. I know we kind of sped through this section, but like I said, at this point, you're becoming a pretty sophisticated smart contract engineer. And I really wanted to show you the process of voting of a typical DAO from today, and for you to see it from the coding side as well. Now, if you want to go further with this, I highly recommend you look into some of the different methodologies and some of the newer methodologies that researchers are coming out with for people to actually do votes. Because like I said, plutocracy is not the best. So if you want to go farther, try experimenting with other ways to build DAOs. Maybe flesh out your own DAO. Maybe deploy a DAO. Do whatever you want to do here. But in any case, you should be incredibly proud of yourself because you got through the hardest lesson of this whole course already, which was the stablecoin one. And then you just learned this incredibly powerful advanced course in how DAOs actually work.